All right, welcome to the trapezoidal rule, which is 5.5 in our textbook. All right, so what is the trapezoidal rule? Well, this is a method for approximating the area under a curve using, guess what kind of shape? Trapezoids. So we looked at using rectangles to approximate area under a curve in section 5.1. Well, now instead of rectangles, we're going to use trapezoids. So it's the same idea. We have this function between x values a and b, and suppose we wanted to put 3 trapezoids in here, okay, and they're each going to be of equal width, okay. So imagine drawing in 3 trapezoids, okay. So the parallel sides are these y values. So the trapezoid is really turned on its side, okay? And recall that the area formula of a trapezoid is 1/2 the height times base 1 plus base 2, okay? So these bases are really the y values on the function, okay? Again, the trapezoid is really turned on its side. Now, the height here, okay, the height is really our change in x. And our change in x can be found by looking at the total distance between a and b, which is b minus a, all right, divided by however many subintervals, or in this case trapezoids, we need to sandwich in between a and b. Okay, so n, just like before, is the number of subintervals. Now, when we were doing Riemann sums, our subintervals were rectangles. Now, with the trapezoidal rule, our subintervals are going to be trapezoids. Okay, so maybe you're told that there are 3 subintervals. That means you would have 3 trapezoids. Okay, so notice that, let's see here, what was I going to say? Oh yeah, notice that this side here, this base, okay, is only going to be used one time. Notice how this second base here is going to be used 2 times because it's shared by both these 2 trapezoids. This next y value here, this next base or this next height, all right, that's shared by these 2 trapezoids. And then this last distance here is only going to be used one time. Okay, so how are we going to use this to approximate our area? Well, the easiest thing to do is, well, I'm not sure if it's the easiest, but a thing to do is to simply find the area of your individual trapezoids and then just add them together, okay? But there is a little shortcut, and that shortcut deals with knowing that this side is being used once, this last one is being used once, and then the ones in between are going to be used 2 times. So let's see this in action. Alright, so in this example, we are told to use the trapezoidal rule with n equals 4, so we're talking about 4 subintervals or 4 trapezoids, to estimate the area underneath x squared from x values ranging from 1 to 2. So, if we are first looking to find, well, let's jot down our area formula, okay, of a trapezoid, okay? Let's start by doing that. So let's focus in on the height. We know that the height is represented by our change in x. And the formula every time for this is to do b minus a all over the number of subintervals. Well, what is b and what is a? Well, these are the bounds, okay? The a is in the bottom, the b is in the top, okay? So this would simply be the 2 minus the 1 divided by 4. So our change in x, or our trapezoidal height, is going to be a quarter. Okay, so we need to section this off so that we have quarters. Okay, so we are going to be drawing in 4 trapezoids. So let's avoid using decimals here. If we go up by quarters, all right, 1.25 would be 5 over 4. 1.5 would be 6 over 4. 1 3/4 would be 7 over 4, and of course 8 over 4 is our 2. Okay, so let's just get a visual of what's happening here. So what we are going to do is we are going to go up from 1 until we hit the function. We're going to go up from this 5 over 4 till we hit the function, and then we would draw a trapezoid. So we're going to go up from 6 over 4 till we hit the function, connect it over there, and just like with Riemann sums, you're not expected to draw this every time, but excuse me, in the beginning I like to do it just to help you visualize. Okay? So notice how this curve here, because it's increasing and concave up, it looks like our approximation is going to be a slight overestimate, right? Because our trapezoids are just on the outside of the actual bent curve. Okay? So keep that in mind. Alright, so we have, once again, 4 different trapezoids here. So it's helpful to stop and get your table of values. Alright, we want to get the y values for all of these different x's. Okay, so let's do that. Set up a table. Alright, so there's our table of values. Again, our function is just x squared. Alright, so we'll label that on our graph. And our x value of interest, or x values of interest, are those 5 that you see listed there. Okay. From here, we're looking to find our area of all 4 of these trapezoids. So, yeah, you can go through individually and find them one at a time and then add them all up. All right. If you were to do that, you would see that they each have a 1/2 times the height. That is common. Now remember we said that this 1 over 4 is really the h. So that's 1 over 4. Okay. Now, what we're going to do is we're going to work smart here. Let's look at this first trapezoid. Okay. We know that this height is going to get used 1 time. All right. And so this first height was 1. I'm looking at this right here. Plus, now this second height, or the second base on my trapezoid, which is really 25 over 16, that's going to be used 2 times. Okay, it's going to be used in both of these trapezoids that are sharing it. So I'm going to do 2 times 25 over 16, plus this next base or height will get used 2 times. So that's the 36 over 16. Okay, we can keep going. This next height is used 2 times. And then finally, our last base here, which is 4, that's only going to be used 1 time. Okay, so this is my expression here for my area of all 4 of these trapezoids. Okay, now again, if that doesn't make sense to you, you can go through and single-handedly find the area of each trapezoid. Okay, the first one would be 1/2 times 1/4, and then you'd have the 1 plus 25 over 16. You'd have to calculate that. And then you would do, for the second one, 1/2 times 1 over 4, and then you'd have the 25 over 16 plus the 36 over 16. Okay, you could just repeat that, all right, 4 times, and then add them all together. But I'm pretty sure you would agree with me that it's going to be a lot more efficient to just remember that the first height and the last height, these get used once. Okay, the ones in the middle are going to get used 2 times because of that idea of a shared size or shared side. Okay, so let's clean this all up. So when we clean this up front we have 1 over 8, and then if we get a common denominator of 16, it ends up being 300 over 16, which is 300 over 128. If you divide each of those by 4, you're left with 75 over 32, or you get this decimal, and if we round using 3 digits after the decimal, that's what we get. Typically you're going to be allowed to use a calculator for these. If you're not allowed to use a calculator, then the numbers will be very manageable. So real quick, let's compare this to the actual area. So right now I want you to grab your calculators and I want you to enter this in, all right, to fnint, and let's write down what the actual area is to compare. Okay, so the actual area is 2 and a third, or 2.3 repeating, which is a little bit smaller than what we got. So our approximation was slightly bigger. And remember we said because this is increasing and concave up, there's just this little region where the curved part, or the top part of our trapezoid is above the curved portion of our function. Okay, so you can see that there is a slight overestimate. Okay, so that's the trapezoidal rule. Just remember the idea of using the heights on the end, or the y values on the end, just one time, and then all those bases or y values on the inside are going to be used twice. All right, bye-bye.